Okay, so I just wanted to take a minute to go over a few things that I ran out of time for in class and realized that you probably would need. Some of this will be review from your Math 213 class, but I think it's worth just quickly going over it in the context that I consider it important. So we talked a little bit about eigenvalues and eigenvectors. So I just want to do a quick example. So imagine that I have the following 2x2 matrix, and I want to find its eigenvalues and eigenvectors. Well, my eigenvalue equation looks like this. So here's my matrix A, my vector x, and my eigenvalue lambda. So we can do a little bit of stuff that looks like normal algebra. I'm going to take my matrix and my vector. I'm going to subtract off this, and of course that's going to give 0. Now what I'd like to do is do a little distributive property, but I have a problem, which is that A is a 2x2 matrix, lambda is a number, and subtracting a number doesn't really make sense in this context. So I need to take lambda and turn it into a 2x2 matrix, and I do that by simply multiplying it by the identity matrix, which looks like this. And now, of course, I can rewrite this as 2 minus lambda. So my 2 minus lambda times 1, 1 because it's 1 minus 0 times lambda, 4 because it's 4 minus 0 times lambda, and then 5 minus lambda because I've got a 1 in this position and in this position. So really, this guy right here really looks like lambda 0, 0, lambda. Okay, and I wanted that multiplied by my vector x to be 0. Now, if you remember your linear algebra, or if you're willing to trust a teacher here, this will be true if the determinant of 2 minus lambda, 1, 4, 5 minus lambda equals 0. So it turns out this condition here is equivalent to this condition here. How do we solve the determinant? We multiply these two terms and we subtract these two terms. So I get 2 minus lambda times 5 minus lambda minus 4 equals 0. Now I just got a little FOIL action here. 10 minus 7 lambda plus lambda squared minus 4 equals 0. Or lambda squared minus 7 lambda plus 6 equals 0. And I can factor that into lambda minus 6, lambda minus 1 equals 0, so lambda equals 6, or lambda equals 1. We can do the 3x3 case. Well, let's finish this. So here are my two eigenvalues, 1 and 6. Now, what I want to find is a case where, again, A minus lambda I times x, the vector, equals 0. Well, I now know a lambda where this is true. So I take my 2, 1, 4, 5. I subtract 1, 0, 0, 1. Multiply that by my vector, which we'll just call x0 and x1. And all that has to equal 0. So 2 minus 1 is 1. 1 minus 0 is 1. 4 minus 0 is 4. 5 minus 1 is also 4. And now I can multiply that out, and that says that x0 plus x1 equals 0, or x1 equals negative x0. So I can choose any value of x0 I want, and if I choose x0 to be 1, then x1 is minus 1. I can similarly go in and change this to 6 and this to 6, and I solve and I get lambda equals 6. Lambda equals 6 leads to this eigenvector for 1. And so those are the correct eigenvectors. We can test that out. Let's take 2, 1, 4, 5. Let's multiply it by 1 minus 1. And I get 2 times 1 is 2 minus 1. And I get 4 times 1 is 4 minus 5. Which 2 minus 1 is 1. 4 minus 5 is minus 1. And in fact, I get back the same answer multiplied by 1. So we've validated that this is in fact an eigenvector with eigenvalue of 1. Now, commonly, we want to do what's called normalizing our eigenvectors. And you can think about this geometrically. If I have a standard set of Cartesian coordinates, really what we say is, we would call this point 1, 0. It's 1 along the x-axis, 0 on the y-axis. And over here, 0, 1, nothing along the x-axis, 1 along the y-axis. And each of those has length 1. And by the way, you can calculate length as the sum of each of my, we'll call them q sub i's, x and y, squared. Or as you know it, delta x squared plus delta y squared, Pythagoras in fancy language. We're eventually going to want to go to n dimensions, so we need the flexibility. So we want our length. Now imagine instead of those vectors, we wanted to use these vectors. So this vector is going to be 1, 1, and this vector is going to be negative 1, 1. Now if I look at the length of this vector, well, that's going to be 1 squared plus 1 squared, which is 2. Well, the length squared, so I should put length squared there, so length is square root 2. Meaning if I want this to be a unit vector, I actually want this to be 1 over square root 2, comma, 1 over square root 2. And up here I want this to be negative 1 over square root 2, 1 over square root 2. And now when I take 1 over root 2 squared plus 1 over root 2 squared, well, that's 1/2 plus 1/2, which equals 1. So now we've normalized our eigenvectors. And so really I could choose to write this as 1 over square, 1 over root 2, 1 over root 2. Okay, so now what if we want to do a more complicated thing? Let's go ahead and go over to MATLAB here and let's ask if we can do the same thing. So I need to start by, I'm going to define my matrix. So for matrix, we put a square bracket, and I'm going to put my first row, which was 2, 1. And now I need to just go to my second row, so I'll put a semicolon. That tells me I've gone to my next row. And that's going to be 4 and 5. So there's my matrix, 2, 1, 4, 5. And now I want to find eigenvectors. So if I type eig of A, it'll hand me back my eigenvectors 1, or eigenvalues 1 and 6. If I want to have more information, if I want my eigenvectors and my eigenvalues, so I'm going to do E vector, comma, so this particular thing, square brackets, now tells me I'm going to hand back 2 different types of answers, the eigenvectors and the eigenvalues. Command is still eig, and we do eig of A, and it hands me back my 2 eigenvectors. And just to double check, 1 over square root of 2 is 0.7071. So here's my minus 1, 1 eigenvector, and then this is going to be my other eigenvector over here. So now I can do slightly more complicated problems. Let's do another one. Let's set my B vector, and this is going to be a 3 by 3. A 3 by 3, the solution type is the same. I end up with a 3 by 3 matrix, which gives me a third order polynomial. It's a lot of terms, it's doable, but it's not fun. So my first row is 1, 4, 6. My second row is 4, 3, 1. And my final row is 6, 1, 1. Now, here I've created a very special kind of matrix. You notice 4 and 4, 6 and 6, 1 and 1. Call this a diagonal symmetric matrix. The top half is the same as the bottom half. This type of matrix represents a particular type of mathematical operator that will be important in quantum mechanics. So now we're going to go ahead and run our eigen command against the B and have it return eigenvectors and eigenvalues. And you notice this goes nice and quickly. Here's my 3 eigenvalues along the diagonal of my E-value matrix, minus 5.59, 1.44, and 9.1452. And here's my vectors. Each of these column vectors represents 1 eigenvector. Here's 1, and here's 1. One of the special properties of this kind of symmetric matrix is that each of these eigenvectors is going to be what we call orthonormal. So orthonormal has 2 properties. One, let's do normal first. Normal means that if I take the sum of the squares of the vectors, it will give me the answer 1. So I'm going to take E vector, and then I want 1, 1 squared plus E vector 2, 1 squared plus E. So I'm taking 1, 1, which is this guy, 2, 1, which is this guy, and 3, 1, which is this guy. I'm squaring them all, and I'm adding them together. And because it's normalized, the sum is 1. I can actually do this a little more cleverly. I can use the sum command, which sums up values. Now I want all rows, but only the first column. And now I need to tell it to square those numbers. In class, we talked about square can mean one of 3 things: a dot product, a cross product, or the individual elements squared. In this case, I actually want individual elements squared. In MATLAB, the way I do that is I put a period before the caret, which means take a square, or take a power, and my power is going to be 2. So period caret 2 means square each element individually. That's what the dot means. So when I do this, again, I get 1. I can get one layer more clever. I can put this here now. Now this says sum over all rows and all columns of all numbers squared, but I really only want to sum over the vertical columns and sum along a vertical column, and I want to keep each of those columns separately. So I'm going to tell it to sum over the first index, which is the row index, but don't sum over the column index. And so if I do this, it will return 3 1s. That is a 1 for the first column, a 1 for the second column, and a 1 for the third column. So to type it out explicitly, I can use my sum command on a single column, or I can use my sum command on all columns, but I have to specify that I want to sum over columns. So I know that these are normalized eigenvectors. The sum of the squares of the elements are 1. Now I want to show they're orthogonal. If we go back to our idea here of our Cartesian coordinates, obviously x and y are orthogonal. They point in different directions. And if I take my dot product now, and I take 1, 0, and I dot it into 0, 1, well, I get 1 times 0, which is 0, plus 0 times 1, which is 0, and I get 0. But also, if I take my other set of axes, 1, 1, and negative 1, 1, well, I get 1 times negative 1, which is negative 1, plus 1 times 1, which is 1, and I still get 0. So, you shouldn't be surprised. These two vectors are every bit as orthogonal as these two vectors. And now we're going to use this geometric idea of orthogonality to say that if I two vectors and their dot product is 0, we have things that are orthogonal. Switching back here, we can now look at, so E vector, there's my first eigenvector. But in order to do my dot product, I need a row vector times a column vector. How do I turn a row vector into a column vector into a row vector? I simply put a single tick afterwards, and that will give me a row vector. So now, in order to do this, I can multiply it, and I get not 0, but 10 to the minus 17th, which is a pretty small number. Now, for those of you thinking ahead, of course, I can do with the sum what I just did before if I do a dot product of the vector with itself. Let's look at our geometric example again. What if I dot 1, 0 into 1, 0? Well, I'm going to get 1 times 1, which is 1, plus 0 times 0, which is 0, and I'm going to get 1. Note, if I take 1, 1, and negative 1, 1, 1, 1, and 1, 1, and dot them together, I'm going to get 1 plus 1 equals 2. This is not normalized. But if I take my 1 over root 2, and I dot that into 1 over root 2, 1 over root 2, I'm going to get 1 over root 2 times 1 over root 2, which is 1/2. 1 over root 2 times 1 over root 2, which is 1/2, and I get 1. Our definition of normal is dot product gives us 1. Our definition of orthogonal is dot product gives us 0. So finally, I have a way of looking at normal dotted with itself and orthogonal dotted not with ourselves. Let's check 1 against 3, 10 to the minus 16, and let's check 2 against 3, also 10 to the minus 16. So we have generated 3 normalized orthogonal eigenvectors. Now we're going to come back to this idea when we talk about wave functions. It turns out the same rules will apply to our eigenfunctions, which are our wave functions, as applied to our eigenvectors. And we'll see matrices correspond with operators, functions correspond to vectors, and our eigenvalues are going to correspond to our individual eigenvalues.